My name is Benjamin Katz, and in this video lab report, I will be discussing my process, findings, and conclusions of Lab 3 Black Hole Orbit. I will also be walking through the changes I made to a computer model in VPython that determined the mass of a black hole. In essence, we are using an object's motion to predict another object's mass using the fundamental principle of momentum and gravitational force. This differs from what we've computed in labs before, where initial conditions were used to predict an object's motion. Finally, I'll go over the what if and what does it mean lab questions. This will inform how I obtained the ultimate conclusion that the mass of the black hole in my code was found to be approximately 2.99 times 10 to the 31 kilograms. Before going into the actual VPython code for Lab 3, I'll quickly cover the fundamental principles of physics that take effect in the code later in the presentation. First of all, the magnitude of Fnet is equal to the magnitude of dp dt as shown in this equation. This is the basis of the equations in this lab. Next, the only force in this lab is gravitational, and is proportional to the sum of the masses of the two objects. It is inversely proportional to the distance between the objects squared. The gravitational constant, or g, is calculated to be 6.67 e to the negative 11 Newton per meter kilogram squared. The rest of the equations show how the parallel and perpendicular components of Fnet and therefore dp dt can be derived. To begin the Lab 3 code, I downloaded the net force from Stardata start Python file and the Stardata CSV file. These two files allowed me to find the mass of the black hole with the code changes taken into account. The Stardata CSV file provided the different locations for the star as it travels around the black hole over time. Next, I took some initial data components from WebAssign and plugged them into the VPython code. This included a mass of the star of 1.9890 e to the 30 kilograms, the position of the black hole, and delta t, which was 86,400 seconds, or 1 Earth day. After the initial data inputs, you can see here where the code imports the stardata.csv file with the star's location over time. In the first while loop of the code, the velocity of the star is calculated during each time step as it travels around the black hole. In the next while loop, the initial and final velocities of the star are first defined. Next, the initial and final momentums are calculated by summing the velocities of the star and its mass. This gives the result of delta p and delta v. Next, dp dt can be calculated as the change in momentum over the change in time. Because we know through rigorous testing by other experiments, Fnet can be assumed to be the same value as dp dt. The direction of momentum can be found by dividing the initial momentum by the magnitude of initial momentum. This is called p hat. At this point, the magnitude of dp dt is found by dividing the change in magnitude of momentum by delta t. To find the parallel component of dp dt, p hat is multiplied by the magnitude of dp dt. Due to our previous assumptions, we also know that the parallel component of dp dt is equal to Fnet parallel. Then the next step is to find the perpendicular component of dp dt. Since Fnet is its parallel and perpendicular components added together, we subtract dp dt parallel from dp dt to find dp dt perpendicular and thus Fnet perpendicular. The arrow scale for the code, when running, was found by guess and check to allow for an appropriate arrow size. Finally, the gravitational constant, as well as the equation for gravitational force, were added to find the final result of the black hole's mass. The final result is printed at the end of the Python code. As you can see when I run the code, the star travels around the black hole. The size of the arrows, or gravitational force, increases as the star gets closer to the black hole and vice versa. The black arrow is the parallel component of Fnet, the blue arrow is the perpendicular component, and the yellow arrow is Fnet. In a second try, I ran the code with a recurring print statement for the mass of the black hole. Since the mass of the black hole stays essentially the same, the code proves to be working correctly. So what does it mean? The answer to this question is that the Fnet and dp dt equations are equal, but are derived in different ways. Fnet comes from the force of gravity, while dp dt comes from these two equations here. dp dt describes how the star moves, and Fnet describes the star's actual motion. What about the what-if question? If the black hole was replaced by another black hole with another mass, I wouldn't be able to calculate the new black hole mass unless a new stardata.csv file was given. Even still, I would not be able to calculate the new mass because the position values from the first part of the code would be incorrect. Essentially, there'd be no new values of position, and the black hole mass would stay the same. In conclusion, VPython was correctly used to use an object or star's motion to predict the mass of a black hole it was orbiting. This, coupled with fundamental principles of momentum and gravity, were used to find that the mass of a black hole was around 2.99 e to the 31 kilograms.